right, hey guys, Mr. Kyle Myers Mathematics, then let's just jump into it. This is a video where we'll be kind of like, maybe not taking a break is the right word, but just a different video, little palette cleanser from the series on series that I'm doing right now. This is actually a question, and I don't know if I worded it exactly right, but I'll explain kind of how I think it might have been worded a little bit differently, but not that it matters too much, practically speaking. This question is actually a Calc 3 question originally, but we don't actually need Calc 3 to solve it. So the first thing I want to do, well, actually the first thing I might do is, do I have it already pulled up? No, I have something else pulled up. Uh, maybe we'll look at it in the next video. But essentially, we want to find the min and max points on the ellipse. So the point that's the closest to the point 2, on the ellipse, and the point that's furthest away from the point 2 on the ellipse. So we don't need Calc 3 for this. This is like a Lagrange multiplier kind of thing. This is actually a optimization kind of question from Calc 1. We don't really need to go that far into calculuses to solve this, but let's look at it real quick first. If I graph this, and you guys can see that, yeah, the grid lines here. So I'm going off of the grid lines. I'm going to try to keep my lines in the right places here. And there's our x-axis. Okay, so we have our ellipse equation, which if we were to put it in standard form, we would divide both sides by 4. So that would be 4x squared plus y squared equals 4, and I would divide both sides by 4. And I'm going to do that because an ellipse equation has to be equal to 1. So this would be equal to y squared over 4. And that would be over 1 if I wanted to put it as a denominator, which you'll see why in a second, why I would want to do that. But this is proper form for an ellipse. So that means that the x radius is the square root of 1, which is 1. So here and here. And then the y radius is 2, as in the square root of 4. 1, 2, 1, 2. Right? So here's the 4 corners, so to speak, of the ellipse, and I'll try to sketch it out here. It's going to be something like that. It's going to come up here, turn around, and then come back over here. Right? So it's kind of like a little football, a little goose egg, whatever you want to call it. And there's that equation. And then we're trying to see, okay, so on the point 2, 2, 1, 2, 1, 2. Right? Where is it the closest and where is it the furthest away? Well, it's exactly 2 spaces away from the point 0, 2. But I have a feeling that somewhere in here, we'll use a green list, somewhere in there probably is the closest. Somewhere in the range of like 0.8, 0.7, 0.8, comma 1.5, somewhere in that ballpark. And if you look, let's see, like down here maybe like down there somewhere would be about the furthest away. And that's just based on thinking about like, okay, so the shortest distance will be wherever the tangent line is perpendicular. So if you can draw a tangent line on the ellipse, and then that's going to have a perpendicular slope to the line that goes directly towards it, that's going to be your closest point. We don't need to kind of go at it from that angle though. What we can actually do is we can just solve the equation for y and then plug it into the distance formula, because we're trying to figure out the max and min distance, the points that are the closest. So it produces the closest distance. Well, the distance formula is equal to the square root of, and then it'll be x2 minus x1 squared plus, and this is essentially the Pythagorean theorem, is what this is. So here's the distance formula in all of its glory, and we want to find out how far away it is, how far our ellipse is from x and y when those are 2's. So we want the x value when the x value of the point is 2, and then same thing for y. So we want this. Well, this is a function with technically 3 variables, the distance variable and the x variable and the y variable, and that's why this equation can be done using Calc 3 because it's multivariable calculus. We don't need it because what we can do is we can just take the ellipse function and, well, it's not a function, but we can take the ellipse equation and we can turn it into a set of 2 different functions, like a top half and a bottom half, essentially, by solving for y. So if we do that, then we would say, let's actually go back to the original here. And we would just subtract the 4x squared on both sides. So this would be y squared is equal to 4 minus 4x squared. And then if I take the square root, I can actually factor out this 4. So it'd be 1 minus x squared. And then I want to take the square root of both sides. I want to take the square root. So this is going to be y is equal to plus or minus the square root of all of that. And I can take that 4 out then as well. I want to simplify this as much as I can, makes the derivative a little easier. Let's see, do I want to leave that inside of there? I guess that's fine for right now. Yeah, I guess that's okay. So that the plus side would be the top half of the ellipse, the negative side would be the bottom half of the ellipse. So we're looking for a minimum with the top half, and we're looking for a maximum with the bottom half, because we already kind of have the visual to help us out. Since that's y, we can plug that in right there. Okay, I am going to have to scale this out a little bit. So blow this up a little, or actually make it smaller, I guess I should say. We want to make it a little smaller, and then we're going to want to take the derivative. So if we plug that in, then the distance is going to be equal to, and this is x minus 2 squared, so that's going to be x squared minus 4x plus 4. And then over here, that y value is plus or minus, yeah, it's plus or minus. And then I'm going to be squaring it though, so let's do the positive half. So that's going to be, oh, I like move the whole thing over. Accidentally clicked the right arrow key. Hold on, move my watch a little bit so I'm not accidentally clicking buttons. So the y value is, so it's going to be plus parentheses. The y value is 2 root 1 minus x squared. And then that's minus 2 squared. And then all of that is square rooted. Yikes. Okay, so we have all of this. And we want to take the derivative of this. So we want to take the derivative with respect to x. So d derivative of the distance with respect to x. And the reason why we want to take the derivative is because the max value, if we were to graph the distance formula on a graph, it would actually graph so that it has like a high point and a low point, and the high point will be the max distance, and then the low point, the further down, that'll be the min distance. And we're looking for both of those areas. So on this graph, if we take and try to take the derivative of this, oh wow, this is crazy. Before we do, let's clean it up some more, because this is going to be crazy if we try to take the derivative as is. So that's going to be 2 times the square root of 1 minus x squared times itself, because it's squared. Let's go over here. So let's actually just focus on squaring all of this for right now. Let's actually go somewhere where I have some more space. So if we try to square all that stuff out, let me use yellow. If we take the 2, 1 minus x squared minus 2, and we square that, then we're essentially timesing it by itself, right? So we're doing that. So if I FOIL it, it would be 2 times 2 is 4. The square root times the square root means the square root squared, which would cancel, and I would be left with that. Right? 3 squared is 9. The square root of 9 is 3. So 3 squared square rooted is 3. If you square something and square root it, you're doing the opposite operation. It's canceling out. So the square roots get times together. They become squared. It's a squared square root. It's a mouthful. I know. Then this is going to be minus 4. And then that's just going to be a square root, because that's going to be minus 4 and then a square root of 1 minus x squared. Then I'll have another minus 4, so that's a total of minus 8 minus another minus 4 square roots of 1 minus x squared. And then minus 2 times minus 2 is going to be plus 4. Okay, so then I have all that. And that can clean up a little bit as well. That's going to be 4 minus 4x squared minus 8 root 1 minus x squared plus 4. Yeah, you guys can still see that. Okay, and then that'll simplify a little bit more. I can put the 4's together. There we go. Okay, cool. So that's about as much as that'll simplify. And then I can add that with some other stuff. So I kind of want to put the squared value of x in the front maybe. So this will combine with that. So that's going to be a minus 4 and a plus 1. So it's going to be minus 3x squared. All right, so we got those. Then I have an x term that won't really combine with anything else, so that'll just be minus 4x. The 4 can combine with 8. 4 and 8 combine to 12. All right, so I got rid of those. And then the only thing left is this square root thing, and it is a minus square root. So that's going to be a minus 8 square root of 1 minus x squared. And actually, because I'm about to take the derivative, let's go ahead and rewrite this as a 1/2 power. So it's 1 minus x squared to the 1/2 power. And then all of this is to the 1/2 power. Yikes, okay. So that's, we still haven't taken the actual derivative yet, but let's go ahead and do that. So the derivative squared, the derivative of the distance with respect to x, will be, so power rule comes first, 1/2. All right, so 1/2, and then you would have all the inside stuff would stay the same. So it's going to be negative 3x squared minus 4x plus 12 minus 8 times 1 minus x squared to the 1/2. Okay, that's the first part. Then chain rule, we times by the derivative of the inside, times by the derivative of the inside is going to be negative 6x minus 4. The 12 is a constant, so that's just going to go away. And then over here, if I'm going to take the derivative of this, I'm going to have another chain rule. So that's going to be a 1/2 times by the 8 gives you a minus 4. And then that's going to be, keep the inside the same, power minus 1. Let's see. Oh, you know what? Did I forget to do power minus 1 on the other thing? I did. That's a negative 1/2. I meant to put that there. I totally meant to put that there. So that's a negative 1/2. I don't know if you can see the negative. It's there. Negative 1/2 power. It's there. Okay, so 1 and then power minus 1/2. Or power minus 1 gives you negative 1/2. Okay, anyways, so times by the chain rule, negative 6x minus 4 minus a 4, because I times by the power, and then keep that the same, and then that's power minus 1, and then that's the derivative of, well, not quite yet, actually, because then it's power minus 1, and then I times by the derivative of the inside of that, which would be negative 2x. Then that'll about do it, I believe. Okay, let me double check here. So I did power rule times by the power, and it'll be power minus 1. You keep the inside the same. Then we do the derivative of the inside, which is going to be all of that stiff on the inside. But while I'm taking the derivative of the inside, I've got to take the derivative of this, which is another power rule, but then I have to times that by its inside derivative. So it's literally a chain rule within a chain rule. That's pretty crazy. But hey, we're done now, so there you go. If we clean this up, I'm just going to call this d prime. If we clean this up a little bit, there's a 2 in the denominator. That's a negative power. So that's actually going to belong in the denominator. This is kind of like a numerator, but it has a denominator in it. So we've got a lot of cleaning to do here. So let's see. That would be negative 6x minus 4. That's going to be minus 4 times minus 2, which is going to be positive 8x plus 8x over, just this part is over the square root of 1 minus x squared. And then all of that is the numerator, because all of this is being times. Just this part is the denominator. The negative 2 got times by the negative 4, that's how I got the 8. And then all of this is going to be over 2, which I got from right here. And then all of this is to a negative 1/2 power. So it's all the square root of all this stuff. 3x squared minus 4x plus 12 minus 8 square root of 1 minus x squared. Okay, I'm going to have to start scrolling over here because this is getting crazy. So we're going to scroll down a little bit, actually. Let's go. Actually, let's just scroll down a little bit for right now because I'm over on the right-hand side. Let's do this. Let's scroll even more. So we're going to move this over here. Yeah, we're going to do that. I like this. I like this. Okay. So this is our derivative. And remember, we're looking for the max and the min values. So we want to set the derivative equal to 0. So that's essentially what we're going to do. We do have a little bit more cleaning to do here. This is a squared inside of a square. I know that's not fun, but hey, it is what it is. So I'm actually going to make this so that it's not a fraction within a fraction. I'm going to times by the square root of 1 minus x squared. Square root of 1 minus x squared. And that'll get rid of the fraction within the fraction stuff here. Let me move this down a little bit, actually. Yeah, let's do that. Let's do that. Okay, I like this. All right, so then the reason for doing this is so that I can get rid of the fraction within the fraction. It's a little crazy. So let's see. So if I multiply, I'd have to distribute this into everything in order to keep it even. So that's going to be negative 6x root 1 minus x squared. Then that's going to be minus 4 root 1 minus x squared. And then here, the square roots of 1 minus x squareds cancel, and I just have plus 8x. There we go. So now there's not a fraction within the numerator. And then in the denominator, that's already kind of all one thing anyways. I could write it all as 1 square root, and that actually could be a little bit help. Kind of not. I don't know. It's just a big old mess down there. It's just messy. So it's gonna be, let's go ahead and do it, because you know what's the worst that could happen, right? 2 square root. So I'm gonna put these 2 square roots under the same thing here. So the 1 minus x squared part will go right here, and then the rest of it will go right here. I am timesing them, so it's gonna be timesed. Minus 3x squared minus 4x plus 12 minus 8 root 1 minus x squared. Okay. So now I have all that. Oh, and everything divides by 2. So I kind of want to do that because that'll be nice to just have everything divided by 2. So if I divide that by 2, it would get the 3. That by 2. That by 2. That by 2 would just be 1. So that's at least we're making a little bit of progress here. Oh, you guys can see that. Now you can see that. Okay, we're setting this equal to 0. So if we're setting this equal to 0, basically the whole denominator doesn't even matter anymore. Because if the denominator is equal to 0, that's bad. So like if x is 1, that can't happen. We can't have x equal to 1. We also can't have x equal to whatever else might make this denominator equal to 0, but that's a little bit easier to spot. I can't have that equal to 1. I also can't have a square root that's negative. So there's a lot of things I can't have here, but I already kind of know my constraints because of the ellipse. I know that the ellipse only goes from the x values of -1 to 1 and the y values of -2 to 2. So I already kind of know my constraints. I don't really need to worry about them. So I don't really need to worry about this denominator at all. So it actually really wasn't that helpful that I combined everything down there. If I set this whole thing equal to 0, I could just times both sides by the denominator and it just goes away. So I'm going to do that. I'm going to set the whole thing equal to 0. The whole denominator goes away because I can just times both sides by the denominator. And it just goes poof. Right? So this is going to be negative 3x root 1 minus x squared minus 2 root 1 minus x squared plus 4x. Right? This is no bueno. This is a no bueno thing. I want to try to get the square root isolated so I can try to turn this into a polynomial if at all possible here. In order to do that, I'm gonna need to factor it out. So I'm gonna minus the 4x from both sides. So that'll go away. I'm gonna minus that 4x on both sides, and then I'm gonna factor out the 1 minus x squared, so that what's left is minus 3x minus 2. And then if I divide both sides by that, so my goal here is to try to get the square root part isolated. And then that way, what I can do is I can just square both sides. So I can do this squared, right? I can do this squared equals to 1 minus x squared. And now everything can just be a nice, neat polynomial. So remember, I'm trying to solve for x here. So I'm going to move this over here. That way we have more space. So that's going to be a 16x squared over, and then if I square this bottom part, I'm actually, I think I might just, because if I factor out a -1, that would be a -1 and then a 3x plus 2. And the -1 squared is just +1, right? So I can make that positive. I want to keep things positive if I can. So I'm going to times both sides by 3x plus 2 squared. And then that's going to be 16x squared is equal to 1 minus x squared times by 3x plus 2 squared, which is 3x plus 2, 3x plus 2. Okay, so that's what I've got right now. Move this up a little bit. And I want to FOIL all that out. Okay, so then that's going to be, let's FOIL out the 3x plus 2's first. That's a little easier. 3x makes 9x squared. 3x and 2, that's 6x. 2 and 3, that's also 6x. 2 and 2, that's 4. Okay. And okay, so now that's going to be 12x, right? So now let's distribute the rest of it. That's going to be 1 times 9x squared, 1 times 12x, 1 times 4. Then that's going to be minus x times times a positive 9x squared. So that's going to be a minus 9x to the fourth, minus 12x cubed, minus 4x squared. Okay, let's move this over here. So if I put it in descending order, I've got a negative 9x to the fourth, a negative 12x to the third. I've got a couple x4s here, so 9x x squareds. 9x squared minus 4x squared is 5x squared. Plus 12x plus 4. Okay, I want to set the whole thing equal to 0, so that way I'll have everything on one side. And if I subtract 16x squared, that's going to go with the 5x squared, so 16 subtracted from 5, that would be the opposite of 16 minus 5, so that's going to be minus 11x squared plus 12x plus 4. Okay, I have nothing I can divide on both sides that'll make this any easier. And that is a pentanomial, so that's pretty crazy. The only hope for us here at this point is synthetic division. And I'm really, really hoping that something nice happens, but I don't think it is. So what I might do is I might actually cheat a little bit and use some Desmos. Let's see, do I have this pulled up on calculus? Yeah, let me pull this up, and I'm gonna yoink this over to the side, and I'm gonna pull up Desmos over here, and then I'll put it back so you guys can see it. So give me a second. I'm gonna pull up Desmos. So you should be allowed to use a graphing calculator on this. If you're not, I'm sorry. but you know, it is what it is. So I'm just gonna, let's see if I, yeah, I'm just gonna yoink this back over here. Okay, so here we go. Slowly dragging it over. There it is. Okay. And actually, I do want to keep this right here for right now. That way I can see everything I'm putting in. So I'm going to put y equals this function that I've got here. And then that way I can look for its x-intercepts. Because this is just so crazy that I don't know why any professor would enjoy this kind of torture. This is just sadistic. If your professor wants you to do this without a calculator, you need to run. You need to run. Plus 12x plus 4. Okay, so I have a feeling we are going to have x-intercepts, but I also have a feeling that they're not going to be nice x-intercepts, and I might be right. Let's see. Yeah, that's not a nice x-intercept. Those are not nice numbers. They are most definitely not nice numbers. Yeah. Huh, I don't recognize those either. Let's see. Square root of 2 is 1.4. Square root of 3, 1.7. Yeah, I don't know. Those are just crazy. But they're definitely real numbers because they show up. But I have a feeling like these are irrational. I could be wrong because that's a 111 at the end there. I could be wrong. Let's expand this, see if they give us some more decimal places. They just give us these 3. It could be. What would be 0.72111 as a fraction? Let's see if I can make Desmos tell me. Watch this. So that was what point? What was that? 0.72111. Okay, so 0.72. And if I give it a bunch of 1s, I can maybe see if it can change that into a fraction for me. Haha! Oh, that's not nice. Okay, I don't know why I thought that would be helpful. So 649 over 900. If it is rational, this is if that 1 is repeating on the backside there, then this would actually be the fraction. Oh, that's terrible. That's just terrible. So if it is rational, then that's what it comes out to be. This one, and the reason why it could be rational is because I actually see a 1-1 on the end of this guy too. So that makes me wonder if maybe. Let's see. So negative, we'll take off the negative because it doesn't really matter as far as changing it into a fraction. 0.279. 0.279 and then give it a bunch of 1s. Okay, and then change that into a fraction. It's not even the same denominator. I don't know, guys. I don't know if this is. I don't know if this is actually, if these are actually rational solutions. They might not be rational solutions. But that's crazy. So that's what I'm actually getting there for those answers. And if we ballpark it, so let's do this. Let's put these kind of like side by, yeah, let's do this. Let's put these side by side. So I'm gonna do that, and then I'm actually gonna do. What do I want? I want this. Yeah, I want this. Here we go. Okay. I want this over here because I'm gonna zoom out of this. So we got the solutions using a graphing utility essentially. You could try like synthetic division, but that would just be so crazy. It would just be so crazy. Let's look at what our approximations were about. See? And see if we're in the right ballpark here. So these are approximations for x values. 0.72, right? Didn't we say that? You can go back, you can scrub back, and I was like 0.7, 0.8, between 0.7 and 0.8. I'm pretty sure I said that. Go back, you can check me. But I'm pretty sure I was like, yeah, it's definitely between 0.7 and 0.8. And it was. That looks like that's a good answer because it does look like it's in that ballpark there. Halfway is going to be about right there. You see that? Can you see that mouse? Yeah. So halfway is about right there, guys. And then 0.6, 0.7, yeah, right there. That's about 0.7. And that is what we're getting. So that looks good, actually. And then remember, this was a negative number. So negative point, almost 0.3, that's about a quarter. right? Negative a quarter, right? 0.25 would be exactly a quarter. So that's just a little bit more than a quarter. If we do a half, mine's a little off on this one. So the half would be about right here. A quarter would be about right there. So it's actually a little bit further down than where I put my x. My x is a little off on this one. All right, so I was a little off. My x should have been a little bit further down. But that's still pretty good. And those look like they're correct. Right? Because you can kind of tell just by looking at the graph. Like and I'm not saying that this is like a foolproof thing, but it is good to check your work and make sure that it makes sense. Because if you made a math error somewhere along the way, then most likely the answer isn't going to make sense. It is possible to make a math error and you still be in the ballpark of the right answer, but it's way less likely at that point. I mean, your chances of getting the right answer, we've taken our chances of getting the right answer and we've like skyrocketed them, okay? Because this is looking pretty good here. If these are fractions, these are the fractions they would be. I don't know if they actually are, because again, Desmos doesn't really tell me that. They just give me this decimal approximation number here. They both kind of end in some ones, so they could be rational. I don't know if they actually are. All right, but they're going to be about there and about there. And if we want to know where on the ellipse, we would just plug in these numbers. So again, I would probably use a graphing calculator for this. But you would plug in those numbers. I'd probably plug in at least 4 digits, maybe like negative 0.2791, and then for this one 0.2711, like four digits maybe, because we're gonna have to round on top of rounding, and that's not usually super good. You don't want to round until the end if you can help it, but we kind of can't help it here, unless we want to try synthetic division and just like turn our brain into mush. This because these are the answers that we would be getting here. So if we plug those back into the ellipse equation, we would get the y values of those answers, and then that would actually be it. And I'll probably end it here. If you actually want to see what those values look like, then just let me know in the comments, and I can finish solving it out. I'm actually going to probably do another video where I show how to do this using Lagrange multipliers for Calc 3. But this is actually a Calc 1 method that I just did. So this is helpful for Calc 1. But I'll do another one like it where I do a Calc 3 method. All right, so I'll probably cut it here, but check out that other video if you're interested in the Calc 3 method. And you can check out my website for more resources, myersmathematics.com. Got a lot of cool stuff in there, like the 5 math mistakes everyone makes and how to avoid them. So go check it out. Hope that everything is helpful, because that's what I'm here to do. I'm here to be helpful and teach you guys some math, hopefully in a way that you can understand. So without further ado, we'll end it here, and I'll catch you in the next video. Blessings, y'all.